Just imagine that you are dropping an object from a certain height. What is the velocity with which the object moves after a certain duration of time at a given time t? And also, what is the distance the object would have moved from the reference axis after a certain specific duration of time? Now today, that is what we are going to do. We are going to derive an equation that is going to give you the expression for velocity after time t, and also it's going to give you the expression for displacement after time t, which means we are going to derive an expression that tells you exactly what is the distance the object has moved after a time t from a specific reference axis. You can find all this from the initial conditions and also from the simple equation for acceleration. So I'm just going to start by writing the equation for acceleration. There is a little bit of background life here, so please excuse me. So let me start with the expression for acceleration. Acceleration, let me denote that as A, is change in velocity with respect to time. And you know what is the expression for velocity? It is change in distance with respect to time. Okay? So U here stands for the distance. Now, what I'm going to do is I'm just going to plug the value for V, right? Expression for V in this acceleration equation. So that is going to give me the expression for acceleration as d by dt. Mathematics is just like moving objects. I'm going to take this value of V and I'm going to substitute it here. It's going to be du by dt. So I'll be getting d square u by dt square. So that's the expression for acceleration. Now I can write this expression for acceleration, d square u by dt square is equal to acceleration. Now what I'm going to do is I'm going to multiply by dt on either side of this equation. So if I multiply by dt on the left side of the equation and I also multiply by dt on the right side of the equation, I'm not going to do any damage to this equation. Immediately you can see that this expression on the right hand side, if you work out the units, it's going to be meter per second, which means that when you hit an acceleration term with a time term, you are going to get the expression in terms of meter per second, which is an expression for velocity. We are almost there, but we want to get an expression, a generic expression for velocity, an expression that gives the velocity at any instant of time. Okay, so what I'm going to do is I'm going to integrate this expression on either side. Integration is simply summation. So let me integrate this expression on either side. So let me integrate this. So if you integrate this with respect to time, you are going to get du by dt, and on the right side it's going to give you at if you integrate acceleration with respect to time, plus there is going to be a constant of integration which is going to be c1. This is the expression for velocity. So this is the expression for velocity. So you can use this simple equation to find the value of velocity at any instant of time, provided you should know the value for c1. So let me put a nice box there, but not yet because we have to find the value for c1, but still I can just draw a box around this equation. Okay. Now I'm going to multiply by dt again on either side. So let me multiply by dt so that I'm not going to do any damage to this equation again. So clearly you can see if I multiply by dt, this is going to give me an expression for displacement, that object moves at a small duration of time dt, but I want to find the distance the object moves for a substantial duration of time. I'm not sure whether I can use the word substantial here, but say for a duration of time t, after a duration of time t. So let me multiply first by dt's on either side, so I'm not going to do any damage to this equation. That allows me to integrate and to find the expression for displacement. So I'm going to integrate this expression on either side. So if I integrate this expression on either side, So I'm going to end up with the equation for velocity, for equation for displacement u is equal to, if I integrate this expression, I'm going to get a into t square divided by 2 plus c1 into t plus there is going to be a constant of integration c2. So this is going to give me the expression for displacement at any instant of time. All right. So now I have got an expression that gives me the velocity at any instant of time if I drop an object from a certain height, or an object that is subjected to a constant acceleration. Also, this expression is going to give me the value for displacement at any instant of time. Now, how do I find the value of C1 and C2? Simple, by applying the initial conditions. Just imagine that you are dropping an object from a certain height, okay? Or you need not drop an object from a certain height. It may be an object that is already falling from a certain height, okay? So let us say that this is the axis. This is going to be your x-axis, and this is going to be your y-axis, okay? So this is going to be your y-axis. And let us say that the initial distance that you start this object with, that you start measuring, let us say that the initial distance that the object has moved from the reference axis, let us say that it is u naught, or you can also call that as ui, maybe preferably u naught. That is the initial condition. And also the distance, the velocity with which the object is moving, right? Let us say that it is moving with a velocity of u naught dot, okay? So u naught dot is the velocity with which the object is moving. So these are the initial conditions. Suppose if you are starting this object from this point, then definitely this object's initial displacement is going to be 0, okay? But we want to come up with a very generic expression. So let us assume that there is an initial displacement, okay, from the reference axis. And also you can say that when you are just dropping the object from this axis, its initial velocity is also going to be 0. Okay. Now what we are doing is we are just assuming that it has moved a certain distance u naught and its initial velocity is u naught dot. All right. Now let me substitute these initial conditions in the expression for velocity. So here is the expression for velocity. So at time t is equal to 0, you start measuring at time t is equal to 0 from this position, okay? At time t is equal to 0, what happens to this term? This term actually vanishes, okay, becomes 0. So that gives me the value of c1, and the velocity v is u naught dot. So that gives me, that surrenders me the value of c1 as u naught dot. Okay. Now let me substitute the initial conditions for the expression here. Maybe I can call this as star equation number 2. I can call this as star equation number 1. So let me substitute the initial conditions in star equation number 2. What is that I will be ending up with? At time t is equal to 0, the first two terms disappears, which means these two terms will disappear. I'm going to get the value for displacement u. For the initial condition, it's going to be u naught, that's right, equal to c2. So that surrenders me the value of c2. Having computed the value of c1 and c2, I can now substitute them in the star equation 1 and 2 to get the expression for velocity at any instant of time, which is going to be at plus c1, which is u naught dot, similarly the star equation number 2, that becomes u is equal to at square divided by 2 plus u naught dot into t plus u naught. So that is giving us the expression for displacement at any instant of time. So this is going to be our star equation number 2. Okay. Now you can use this equation. In the next video we are going to code up this equation in MATLAB, and we will see what is the distance an object moves when it is subjected to a constant acceleration? Let us say that it is acceleration due to gravity g. But also note that we have completely ignored the drag, which means the air resistance. With the air resistance into account, if you are considering air resistance, only then you will be able to accurately describe the distance. Okay, so this is the equation for that will actually tell what is the distance an object moves after a specific duration of time when there is no air resistance. Okay, but anyway, we will code up this equation in MATLAB, and we will see what is the distance, how the graph would evolve with respect to time. Okay, now surprisingly, these equations, these simple equations, will be very useful in case if you are a mechanical engineer understanding the concepts of spring mass damping system. We can manipulate this equation a little bit to describe how a mass would move in a spring mass damper system. Surprisingly, we will see how to manipulate this equation to describe the movement, to capture the dynamic response of a spring mass damping system also. Thank you all for your patience. Thank you so much.